So good afternoon. I am D.K. Panda from Ohio State University. This is a joint work between myself and my colleague, Dr. Jiaohui Lu. So today I'll be talking more on the how do you accelerate TensorFlow with RDMA networks to obtain very high performance deep learning. But before I go into more details, I mean, how many of you are using TensorFlow? Okay, quite a lot. How many of you are familiar with RDMA networking, like InfiniBand, RoCE? Okay, some of you, okay. So we'll try to see, like, you are using TensorFlow and how we can really accelerate it on modern HPC clusters. So that will be the focus of this presentation. As many of you might be knowing, I mean, we're in an exciting field of this deep learning, and we know, like, from deep learning is like a subset of machine learning. Machine learning is a subset of AI. And this field is becoming very hot because of three things happening. Over the last several years, a lot of newer models are coming up. These are the models to provide very excellent accuracy for deep and convolutional neural networks. A lot of publicly available data sets are being available. And also, the underlying system, whether it's a multi-core processor or GPUs or high-performance networking, they are providing the capability. Okay, in that context, we are trying to go into all different disciplines and then trying to see how the deep learning can help. So here it shows an example, just like the handwritten digits, how a machine can detect the handwritten digits. You can convert this into this kind of a deep neural network. And once you achieve that, and once you train it properly, then after that, any new handwritten digit can be automatically recognized. Okay, so that's the kind of the framework. So in this context, of course, the big data has become also very integrated to the deep learning, because to achieve deep learning, you need a lot of data for training, okay, and also validation. So these two fields are merging now. So this also tries to show another example of like a Flickr. If you see like a Flickr's magic view photo filtering, you take all kinds of pictures, but then how do you label them, or how do you categorize them or catalog them? And this is a very, they have the solution here from your camera roll automatically detects, like saying these are the sunsets, these are the landscapes. Automatically the machine is able to detect and categorize them properly. So these are the kind of the examples of the multiple deep learning stacks. Many of you must be familiar. There's a long list kind of things starting from TensorFlow to Caffe2, Torch, etc. And from here, if you try to see, this is like the three most important things which are picking up the trend. If you take a look at like this, the Google search trend, I did like last month. So here you see the TensorFlow is on the very upward trend, and that's what we are talking here. So in this bigger context, now, as you said, like some of you are using the TensorFlow, but then as the data size becomes bigger, the model becomes bigger, you need some kind of a high-performance computing platform together with big data. So this is the kind of a new ecosystem which is evolving. So the HPC environment is powering big data, the big data is powering deep learning, and as we come up with a better model, we require more power. So we are in a very good cycle here, and we'll continue to be in this cycle for the next several years. And in this context, there are a lot of challenges coming up, like how do we achieve convergence? That means on the same platform or using the similar kind of a software stack, can I actually achieve HPC, big data, and the deep learning? Okay? Because many times you might be seeing there is an HPC cluster sitting here, there's a big data cluster there, you're doing deep learning on here, so you keep on moving data between all these machines, and those are not efficient. So the question is, how do we put them all together into the same machine? So this is how the overall framework is evolving. So if you see at the top level, we have all the different kinds of deep learning models and the big data sets. This is what we talked about, the TensorFlow. So this is trying to be built on two pillars. So this is the side of the big data. Many of you must be familiar, like these are the typical Hadoop, Spark framework, the resource scheduler, file systems. But a lot of exciting things are happening on this side. That is the HPC, or the high performance computing, is trying to bring. First of all, for all these deep learning, the neural networks, you need some kind of this math operations. And this is where it is happening, either on a multi-core CPUs, you have the MKL BLAS, or even NVIDIA QBLAS, or Intel Math kernel library. And then these are the, especially for NVIDIA GPUs, we are having this NVIDIA CUDNN continuously being evolving. Also the Intel MKL DNN, that is also happening since last year. And finally, this is where like the high performance computing technologies are coming. Two important technologies are coming. One is an RDMA, and then the next one is the GPU direct RDMA. Okay? The RDMA, as I asked, some of you are familiar, the RDMA stands for remote DMA. So that means traditionally within the computer node, we used to have DMA. I mean, it's still there. The DMA allows for the data to move between memory and I/O without involving CPU. Okay? So this RDMA technology came almost 17 years back. I'll talk a little bit about that later, to move data from one node, memory of one node, to the memory of other node without using CPU or using very little CPU cycles. Okay? So that technology came with InfiniBand, and then after that it has got migrated to all kinds of modern networks these days. The other technology which is coming, how many of you have heard of GPU direct RDMA? Not many of you. Okay? So this is the technology which has been there for last several years. The broad idea is that if you have a GPU sitting here, and let's say there is a network card sitting here, most of the time, traditionally, the data used to go to the memory and then come back. But now the idea is that they're sitting on the same, let's say, PCI Express Gen 3 bus. You can actually move data back and forth very easily. Or, in fact, you can now extend the idea that from another node, if I want to send the data, it directly comes over the network and then directly goes to the GPU. Okay, it doesn't have to go to the memory. So these are the kind of the newer technologies which are coming to actually accelerate the communications in a high-performance computing environment. So with that kind of a background of what is happening in the field, I'll try to focus in this talk on these 4 things. I'll try to go into a little bit of more details of the gRPC architecture, the TensorFlow architecture, and also a little bit more on the RDMA technologies. And then the challenge will be, how do we accelerate not only the lower layer, that is the gRPC, and also the TensorFlow, because that is the kind of a combination most of the time people run over traditional Ethernet kind of an environment. So the question is, can we have some good designs which will run all these next generation HPC systems efficiently? And then if we want to do that, then how do we benchmark, and then what kind of performance benefits we can get? So that is the kind of the presentation flow will be. So how many of you are familiar with gRPC architecture? Okay, very few. Okay. So this is how the gRPC looks like. The gRPC, as the name stands, like a Google RPC. So that's how it started from Google. And broadly, you can think of like these are, let's say, these are the clients. These are the server. So you basically like send a protocol request, and then you get a protocol response. It's as simple as that. It's an RPC, remote procedure call. So the client sends a request, and then the server replies back. And this was like developed by Google, and then being used by, after that, a lot of other kind of environments have started using it. And then, of course, TensorFlow is one of the bigger users of that gRPC. But below, if you see, the stack you go down, it uses the sockets. That's the standard sockets with TCP/IP kind of thing at the very lowest layer when you want to try to send request to the other node, and then it come back. So then if you take a look at the TensorFlow architecture, again, some of you are familiar with this. So at the top level, we'll be seeing like all these are the clients, the APIs, and this is where like the inside all these kernel implementations, there are distributed master data flow executors sit. So now the question is, if I have a system with not only CPUs but GPUs, also the networking layer, we have the RPC and then the RDMA. So how we can actually accelerate this part to run on these modern systems, and then that is only the TensorFlow layer, and then if we go into the gRPC layer, that also we can accelerate. So then we can get the benefits from both the layers. So that's what if we put it like together like a gRPC with TensorFlow, this is how it will look like. We have the client, then it goes to the master, and then these are the workers, and not only like the master is communicating with the workers themselves also communicate, okay, because these are the models are running across different nodes, and they have a set of CPUs and GPUs, and they are also communicating here. And in this context, so we need to optimize not only these communications, we also need to optimize these communications. Okay, so then we can get the bigger benefit. So now let's take a very high-level look at all the modern HPC cluster. How many of you at least use some type of HPC cluster? Some of you, okay, good. So this is what you will see the trends are coming there. Of course, we have multi-core, many-core processor. We have accelerator, especially the NVIDIA GPUs. And nowadays, FPGAs are also coming up. And then there is a lot of things are happening. There is a storage also, a lot of excitements are happening. One of the emerging one is called NVMe SSDs. Okay, so the broad idea is very similar to, as I said, like a GPU direct RDMA. You can move data back and forth from GPU to network without going to the host. Same thing you can now do with SSDs also. So think of an SSD and the network sitting next to each other. They can sit actually on the PCI Express bus. So I can send data from one node through the network directly to the SSDs without touching the CPU. Okay, so that actually provides a lot of newer kinds of capabilities to redesign your software stacks to get good performance and scalability. And in this context, all these RDMA things started with this InfiniBand networking technology. I'll show a little bit later a little bit more into details. And then, of course, a lot of other kinds of things are happening. And this is what you see in a lot of these modern systems. If you take like a traditional HPC clusters or even Microsoft Azure, EC2, all these kind of environments are using these all high-performance networks with kind of the capabilities. Now, this is a dense slide, but again, I'll ask, like, how many of you are familiar with OpenFabrics software stack? Not many of you. Okay. So what is happening with these modern networks over the last 18 years, just like you think of the Linux being developed in an open source manner, similarly, all the network drivers are also being developed in an open source manner. Okay. And the organization which is trying to do that is called OpenFabrics. It started in the beginning when InfiniBand came into the market. It started with Open InfiniBand. Then after that, other organizations like IORP and all joined. That's what is known as OpenFabrics. Okay, so the broad idea is that it's a lot of different kinds of combinations these days you see in the modern HPC cluster. Broadly, you can categorize them into two parts. Like one is this traditional Ethernet part. So if you think of like you have an application / middleware, put it like here. So think of like a TensorFlow might be a middleware, and you are using your application running on top of TensorFlow. Okay, so if that is going through sockets, and that's what is the current state of the art, most of the time people use that, you can actually utilize this. Let's say the very leftmost is the Ethernet family. So you typically go through TCP/IP, Ethernet driver, Ethernet adapter, Ethernet switch. When InfiniBand came, it also had the similar kind of things. You can run the sockets over InfiniBand, and it had a mode like a IP over IB. It still has is like an Ethernet emulation. You can think of, or the sockets emulation, so you can run. And of course, as you know, some of the Ethernet hardwares are also have acceleration, hardware offload, those kind of things you can try to run. So that is the kind of the left-hand side. What the InfiniBand brought to the picture is the right-hand side. Okay, so this is where the RDMA, as I indicated, it was built in to the network technology, and then it goes through your user space. Instead of going through kernel, it tries to do a kernel bypass. So you do the communication in the user space mode. It goes through InfiniBand adapter, InfiniBand switch. Okay, so this is the rightmost thing, is the very best performance you can get. Okay, but there is a catch that sockets directly cannot run here. Okay, so what it provided, something called a VERPS, which is you can think of as a very low-level communication layer or a networking layer. Okay, so what it means that my traditional stack, whatever was written with sockets, some portion may need to be rewritten. Okay, if you can rewrite the very lower portion from the socket side to the VERP side, then you should be able to actually run it on all these, the right-hand side, and trying to get good performance and scalability. So that's how InfiniBand brought into the market 17 years back, but gradually it has all the similar concepts has come to another technology called RoCE. I'll talk a little bit about that, IORP. So gradually, a lot of modern networking stacks are actually falling into the right-hand side. So this InfiniBand technology has been there for like 17 years. It got introduced in year 2000. If you now try to see the top 500 list, so that is kind of the every year, like this, the 500 supercomputers in the world get tabulated. Twice it happens. Once in July in Germany, it actually happens at the ISC conference. It will happen in another 2-3 months. And then another one happens in the supercomputing conference in US. Okay. So now if you see, actually, these are the kind of 32% of the top 500 systems actually use InfiniBand. If you see, like even in the top 50, there are 17 systems. In fact, one machine which is not listed, but it is being used, InfiniBand is the actually #1 system in China. Okay, that is like leading the 100 petaflop system. That's the lead system in the world these days. But somehow they don't, when they claim that that is proprietary network, but if you go inside, you will see that is nothing but InfiniBand. Okay, so when it has been entered into the database, it has been put it as a proprietary. Okay, but if you follow all the things, whatever people have found out last 2 years, it's directly InfiniBand. So you can think of like InfiniBand has gone into the #1. So that's how like the technology started in year 2000. Now if you look at the performance, the latency, like the time to take data up from one node to the other node, especially for small message, is less than 1 microsecond. Okay, so think of that kind of a performance I can get. And over the years, InfiniBand has been bandwidth-wise, it's also moving ahead. So currently, it has like the usual one where it's been deployed is 100. 200 has been announced 7 months back. So you'll be seeing the products coming out very soon from node to node. But more importantly, the third metric, which is becoming very important, is the low CPU utilization. Because what happens when you are trying to do all these networking protocols, most of the time, the CPU takes a lot of burden. But then if the CPU is spending a lot of time in doing the network protocol processing, very little cycles are left for actual computation. Okay? So these kind of modern networks try to offload, to think of like a very intelligent secretaries. You might have the executives so that you can offload a lot of things, and then the executives are free to do their computation. So that's what is happening. So with 5 to 10% cycle, you should be able to handle this kind of network protocol processing. And then, of course, that RDMA I talked about earlier. So that has led to like you can do actually RDMA read. That means I can actually, while jobs are running, I should be able to like from my node, I should be able to go to your node and grab data from your memory, or in return I can do a put, write the data. There are of course some synchronization semantics and all, but if you rewrite the software properly, you should be able to get a lot of overlap between your computation and communication, and even I/O. So that's the whole kind of the new storyline, what is emerging for these modern networks. So then, that technology is gradually moving. How many of you have heard of this RoCE? Okay, a few. So this is like a RDMA over converged enhanced Ethernet. So what is happening is, even though RDMA started with InfiniBand, a lot of people want to use that in the Ethernet world. So broadly, you can think of it as like a InfiniBand software with Ethernet hardware. Think of like that. Okay. So it's the Ethernet hardware. If you are familiar with Ethernet, your adapter and fabric can all be Ethernet, but the software is like RDMA-enabled InfiniBand software. Okay, so we are trying to bring both these things together, and a lot of newer deployments are actually trying to take place with this. So the differences are, if you think like this is the InfiniBand, it goes through verbs, transport, network layer, and then here the RoCE, there was a V1, and now there was a V2, that is the very latest, and in fact here it goes, this is what I was telling, InfiniBand software, but Ethernet hardware. Okay, so that's what is emerging, and a lot of new deployments are taking place along that direction. So in this context, in my group, we have been working with InfiniBand for almost like last 18 years. We have a bigger project, which I'm not mentioning here, that is the pure scientific computing, the MPI, message passing interface. That's what gets used all over the world for all the traditional supercomputers. So we have we were the very first one to bring our MPI stack to run with RDMA over InfiniBand. And that has been continuously going on. Even a lot of top 500 supercomputers have been using that. Then six years back, we actually moved to the big data. We tried to take similar kind of approach, trying to bring RDMA to the common Hadoop, Spark, Memcached, those kind of stacks, whatever is being discussed in this community. So these stacks are actually publicly available. So if you go to this HIBD, we call it high performance big data. So we are trying to merge HPC and big data together. And these stacks are actually available for not only InfiniBand, RoCE, they also run on Ethernet. They're available for both like x86, also the new open power platforms that are coming. And the recent releases have also made it available for containers like Singularity and Docker. Okay? So we have RDMA for Apache Spark, Apache Hadoop 2.x, HBase, Memcached. Even it has a lot of micro benchmarks. Currently, they are being used by 280 organizations from 34 countries. And just from our site, there have been more than 26,000 downloads just from our site. Of course, people take these stacks and then integrate with their other software stacks and redistribute. We don't keep track of those. And these are also based on voluntary registration. A lot of people download. They don't want to identify themselves. That is perfectly fine with us. So not only we have integrated stacks, we also have plugins. So for example, like if you are using Hortonworks or Cloudera distribution or even the Apache distribution, you don't have to totally throw away all your installations. We have the plugins. Our plugins can just be used there to accelerate the network portion. Okay? So this project has been there for 6 years. The previous project has been there for like 17 years. And now what I'll be talking, so this is a kind of a thing. You can see like the release time downloads continuously increasing. So then we have moved to now the deep learning, because the field is moving to deep learning. We want to see whether similar kind of ideas can be used to accelerate gRPC and TensorFlow with the RDMA support. And then if we can come up with some good designs, then how do we benchmark, and then what kind of performance benefits do we get? So that will be the next phase I'll be talking. So then the question is, okay, now let's go into the gRPC architecture and then see where we can make enhancements so that we can accelerate it further. So if you take a look at this, like going down to the protocol stack. So if you see here, like this is like your client, this is like your server, this is the parameter server. Let's say this is the TensorFlow worker. So you first request a tensor. Currently, it goes through a gRPC core. It converts that into a set of I/O vector buffers. Then it sends the message. So it comes to the parameter server. It actually does some operation, finds and sends the tensor. It comes back and it comes back. Okay, so this is typically like a gRPC protocol stack. So then what happens is like in a networking terminology, many times there are different kinds of protocols. Some of you might have done the design called a eager protocol or a rendezvous protocol. Okay, eager protocols are for very short messages. So I just send it to you, assuming you have some buffer so that you can hold it on. But if I'm sending very large messages, I can't just throw the message to you because you may not have enough buffers. So it goes through a rendezvous protocol. That means I first check with you to see whether you have enough memory, or if not, then you get send an ACK. If there is enough buffer, then you send an ACK. So those kind of protocols takes place. So then what is happening in the community now, so that is the kind of a bigger challenge. People are trying to accelerate this lower portion. So there are multiple solutions are out there. So there is a Yahoo has posted a gRPC over verbs. You remember I mentioned like the InfiniBand stack, the very lowest layer has to be verbs. So the gRPC has been rewritten with verbs. So then also gRPC, people have solutions with MPI. I indicated the message passing interface, so that library is very common. It has been there in the field for many years for InfiniBand or all these modern networks. So there are solutions there. Even Uber has this Horoword approach. So they have their approach of MPI-based distributed TensorFlow. So instead of going through gRPC, they have totally taken out the gRPC. They just purely go through the MPI stack. That's there. And then also similar kind of thing, Baidu has introduced a TensorFlow all-reduce kind of thing. So these are the kind of the 4 common frameworks which are available there. So we looked at all these things, and we saw that they are not really able to take advantage of the underlying network in the best possible manner, because we have been working on this InfiniBand field for so many years. So that was our kind of a motivation to jump it here. So before we go into solutions, then what we tried to find out, like what kind of message patterns are there? Okay, people have just blindly gone and then say, okay, now let me put it over verbs or put it over MPI. Of course, the solution work, but is that good for all message sizes? Okay, so what we did is we did a lot of characterization. In fact, this paper was presented. The last month there is a BPOE conference. So what we saw that all the traffic, you can actually characterize this into 3 broad categories. I mean, think of like you are sitting at the network level and monitoring all the different patterns of messages going in the gRPC. So here you will see like it can be like a very 3 classifications. We can bring like a small messages, few bytes, medium messages, kilobytes, or very large messages, megabytes. So depending on your model, and of course the end application, you can have a either uniform distribution, that means at some phase you are sending a lot of small messages, okay? Or you can have like a random distribution, it is generating all kinds of messages, small, medium, large in some manner. Or sometimes you can also have a skew distribution. That means what is coming to the network, a lot of small messages followed by large, or very large messages followed by small, okay? So that's how we characterized, or we put it into these 3 bins, okay? So then, in order to have a solution which can handle all this kind of a traffic, so this is where we introduced our new architecture we called adaptive RDMA. So it is adaptive and RDMA. So that means based on the underlying pattern, it can actually select what kind of protocol it wants to use. So we took the gRPC stack, and then we here, if you just think like the protocol buffer request, so this is where we introduced our RDMA engine, okay? So there are some RDMA buffer managements, there are some RDMA endpoint read writes, there are some global buffer pool, we introduced the RDMA communication library. So this is how it will go through the RDMA, adaptive RDMA gRPC core, and then the solutions will come out. And then inside, we had a lot of internal designs, like this is a hybrid communication engine, so that it can handle all the small messages, medium messages, large messages in the best possible manner. We also did some message pipelining, coalescing, some adaptive chunking, intelligent threshold detection, zero copy transmission. So these are the kind of the pure networking enhancements kind of things we tried to brought in based on our prior experience with the big data stacks and then the API stacks. So that's how now the new protocol or the gRPC looks like. So here if you see, like earlier the request tensor, so now what happens, it issues the RPC, but it goes through our module. The yellow one is our module. So it goes through our module, and then similarly on the sender side, it also goes through the same module before it invokes the function and then comes back. So this is where, like on the requester side and then the sender side, we have our modules being placed. So then the question is, once we have the designs, then the thing, how exactly do we benchmark? Okay, so currently also there is a little bit of vacuum in the field. Every time people have a TensorFlow solution, they only run it with the end application or the end model. Of course, that's what we want in the end, but it doesn't give you any insight saying where you are losing performance or where you can accelerate kind of things. So we tried to take a look at a lot of these different models. Many of them might be familiar, like the MINST, CFAR, ImageNet. So these are all the different the benchmarks, then that goes with all these different models. So we did a very in-depth study of all these combinations. So then what we found out, like here if you see like the typical thing what happens, like if you are a deep learning researcher, you take the deep learning benchmarks like what I showed earlier, frameworks, and then you get the result. So this can be like based on your model, it can be taking like minutes to hours to days, okay? So that is good for your end solutions, but it's not good for an architect, okay? Because you don't want to like spend a day, I change one parameter and wait for the next day and then try to come the results, okay? So what we try to do is trying to ask a question that can we actually come up with some kind of a micro benchmarks which will mimic the TensorFlow behavior or the gRPC behavior, okay? So in that case, we can actually take those kind of benchmarks and run it in a few minutes, few seconds, okay? And then try to adjust the underlying system and then see if those kind of newer designs can actually help the end solutions. So that's what we have done. So this is again in that paper I indicated. So we have actually come up with a set of micro benchmarks. So where you can actually change all these parameters, like a number of parameter servers, workers, distribution of IOV vectors, size and number, resource utilization, network configuration. So it is a very small set of micro benchmarks you can play around. So think of it like a sandbox to optimize and tune your underlying environments for both gRPC and TensorFlow. Okay, so that's what we have done. So now let's go move into trying to see how these new designs come up with. So the evaluation has been done in two different clusters. Here there is within my lab, we have an InfiniBand cluster. These are like Intel Broadwell with this kind of RAM. This has InfiniBand EDR, that is the 100 gigabits per second, which is very common for the last several years. And some of these nodes have also 40 gigabit Ethernet. So we can do a comparison between 40 gigabit Ethernet and InfiniBand. Then this is the cluster from San Diego Supercomputing Center. That is a part of the US XSEED system, just like the PRES system in Europe. There is an XSEED system in US for all the academic institutions. So this is again, it has InfiniBand FDR, and then some of them have 10 gigabit Ethernet. So we call them like a cluster A and cluster B. So then we took the gRPC, and we had our adaptive RDMA-gRPC based on this 1.5, and then we used the TensorFlow 1.4. So that's the kind of the exact version we used in our evaluations. So now if you take a look at the kind of results, so what we are trying to show here, like this is the latency of the, like at a micro benchmark level. So these are for small messages, medium messages, these are large messages. So the dark blue line is the default gRPC, whatever is running. And then the red line is actually our new design. Okay? So just at a pure micro benchmark point-to-point latency, you will see that we are able to, our new design, this is on the cluster B, we are able to give you like a, across the board, around 2.5 to 2.8x performance improvement, okay, just for the basic communication. So then we try to put TensorFlow on top of the gRPC. So then this is again like the kind of three distributions I indicated, like uniform, random, skew, and then this is on a cluster A, there is the cluster B. So here again, what we are trying to show, this is the default gRPC that's like on the same cluster. Some of the nodes, as I said, are connected with 40 gig here and 10 gig on that cluster. So this, the green line is the Ethernet. This is the default gRPC over 100 gigabits, and then this is the new design. So as you can see, even the gRPC, whether it runs over Ethernet or even runs over 100 gigabit InfiniBand, performance is very similar, okay? At least on this cluster. On the other cluster, there is difference. Of course, the InfiniBand is trying to give a little better performance, but the more importantly, see the red line. Okay, this is what our design is. So we are able to, like, compare to the, even the blue and the red, they are exactly in the same hardware. Okay, this is InfiniBand running. One is going through the traditional socket stack with IP over IB, whereas the other one is going through the RDMA. And then here we are able to give you like a 59 to 56%, or even sometimes here 69% benefit on this communication. So then that is the kind of a latency. Then we also try to do the bandwidth, like the rate at which we can send. So here it is like the megabytes per second. So here again you can see exactly similar kind of analysis. This is the payload uniform random skew, this side cluster A and cluster B. So you can broadly see like a factor of 2.1 or 3.2. We can give the bandwidth improvement. So then it is not just the latency or bandwidth matters, but especially for RPC or the TensorFlow kind of thing, also we need to see what is the kind of the throughput. How many messages we are able to send per seconds, okay? Because that will determine the overall performance. That's what we did like evaluations of RPC per second. And here again we see, like depending on the different distributions, if the message sizes are uniform during those phases, we can give you like almost 3.4 to 3.6x improvements with our new design. So then we had then we went to a little bit up, the mimic kind of a TensorFlow benchmark, which I indicated earlier. So here again you see, especially for large message sizes, like a 2 megabytes to 8 megabytes, because a lot of these newer models are introducing very large messages. So here we again see either we can get like a 60% reduction in average latency, or in terms of calls per second, we can get around like a 2.68x improvement. Okay. So then finally we went up. So we are trying to do a very systematic evaluation, saying where the performance benefits are coming and how much we can get. So this is finally we took two of the end models. One is the ResNet 50, that is a common model for the TensorFlow. And then here we actually compared all the things, like I indicated, like so far we did the gRPC. We also took the verbs design. We also took the MPI design. And this is our AR-GRPC. Okay? So broadly, and then we systematically, like we had 4 nodes with 2 GPUs on each node. So there are broadly 8 GPUs here, 16 GPUs here, 24 GPUs here. So we are also trying to see the scalability. And then, as some of you might be knowing, when we talk about TensorFlow and all, the batch size also matters. Okay? So how many of the images or the data we are sending it to the GPU at any given time. So the entire, all different workloads will fall into these kind of some characteristics. If you have a workload or your environment, number of GPUs, then you can see, okay, where your things fits in. Okay? So broadly, if you see the red line, that is where like this is images per second. So that means the higher is better. So broadly, we are able to give very sustained improvement across all the other layers. So here we get around like a 44% kind of improvement. And then we go into Inception 3, that is the other model we talked about. So this is where again also we see exactly same like 8 GPUs, 16 GPUs, 24 GPUs. We are able to give like a 24% or 34%, 37% benefits kind of things. Okay, so that's the end at the model level. So this is like a continuing work. We have just trying to do even further optimization on these designs to scale it to even to bigger ones, to run it on a larger system. So with this, let me conclude here. So what we have done in this work is basically like a presented like the basic gRPC TensorFlow. We looked at their architectures and then presented the overview, discussed the challenges. And the broad idea is that how we can take advantage of the modern HPC networking, and then how we can take all those features into the gRPC and then TensorFlow, so that you should be able to accelerate your workload environments. And what I have shown here, these are like the very encouraging results. So this is still in a little bit of research phase. We have not released it yet, but soon you will be seeing, just like our HIBD stack I indicated. Typically, we do like first we publish, and then in 6 to 9 months we bring it out. Okay, so you will see in the next might be this in the middle of this year or kind of things, we'll have a push release so that you people can actually take advantage of it. Okay. So with this, let me just thank all my sponsors and also all my past and current students, teams. I have a very large team working on all these different disciplines, the MPI side, big data side, and also on the deep learning. I also want to indicate this, I've been trying to do this, trying to bring this convergence between high performance computing and big data. There is actually a workshop takes place with a IPDPS, that is the lead conference in parallel and distributed computing. So we have a workshop. The next event will happen in next month in Vancouver. So there are very interesting, in fact, there is a panel there which says which framework is best for high performance deep learning, big data framework or HPC framework, okay, because people are trying to explore along both these directions. So with this, let me stop here, and then I'll be happy to take few questions in the room. Otherwise, I can also discuss with you offline. Thank you. Any quick questions? Yes, please. Okay, so let me repeat. The question is will 200 gigabits improve anything? We have not done the study yet. So the SDR InfiniBand adapters are not publicly available yet. So I believe by supercomputing time it will be available, or in August. Once we get it, we'll do the evaluations and share the results. Any other questions? Okay, so if not, I think we are exactly almost finishing up. Thank you again.